Welcome to Unit 6 on Inference for Categorical Data, Proportions. In this video, we're going to talk about topic 6.3, justifying a claim based on a confidence interval for a population proportion. In fact, it's actually a really easy topic. It's really simple and it's really understandable. But we're going to dive even deeper into confidence intervals and cover a couple different things in this video that are kind of like the final details. So, now that we know the concept behind a confidence interval for a population proportion, and I hope based on the last topic we know how to build one, we can really explore a couple of the few of the finer details that come with confidence intervals. So the four things that we're actually going to focus on this video are: first, what is the meaning of C% confident? I kind of touched on it in the previous topic, but I really want to dive a little bit more into it. We're going to talk about what controls the width of an interval. Then we're going to go into how big of a sample do we need to achieve a given margin of error. We'll talk a lot more about that when we get to that point. And then how intervals can be used to justify a claim about a population proportion. So the actually name of this topic is really just the final thing you see here, but we're going to talk about a couple other things before we get to that. All right, a big question that pops up on the AP test is, what does C% confident mean? So when we're given a level of confidence, and the three most common levels of confidence that you'll see are 95%, 99%, and 98%. These are kind of the three most popular. Again, you could be 90% or even 96 or 92, but these are the most common levels of confidence. So when we talk about being 95%, for example, what does that mean? Well, first and foremost, you really need to understand what we're talking about. Like 95% of what? Because most people just jump and think it's chance. Oh, there's a 95% chance. Like it's a probability. In fact, it actually has nothing to do with probability. It all comes down to a sampling distribution. Remember, we could build a sampling distribution centered at the true proportion P, which unfortunately we do not know. But we can envision the existence of that sampling distribution for the true P. But the idea is this: when we talk about 95%, what we're actually referencing is that 95% of samples are very likely to be near the true proportion in the middle. Again, remember, sampling distributions don't just show one proportion, they show millions of possible sample proportions that exist out there with really big populations. So this model's filled with p-hats. And what we know is that 95% of samples will produce a p-hat that is in this middle area. The only way you could be down here is if you were one of those bottom, significant, weird, super low 2.5% of samples that, honestly, we don't really work with, because I don't want to say we don't work with them, but they're rare. They're significant. They don't happen very often. Or you could be in the top 2.5% that, again, are significantly high. Remember, our alpha value is the total percentage of samples that are unlikely, which in this case is the top 2.5, the bottom 2.5, that's the 5%. Hence, 95% of samples that are in the middle. So when we talk about being 95% confident, it's really truly all about sampling distribution, right? The idea is, if we were to repeatedly look at samples, p-hat after p-hat after p-hat after p-hat, what we know is that 95% of all those samples will be in this middle interval. Now, remember what that means. If we want to be 95% confident, that's from negative 1.96 standard deviations to positive 1.96 standard deviations. So anywhere in that range is the middle or the most likely 95% of samples. Another way that you could look at this is, if I said, okay, guys, we're going to grab one of the proportions. We're going to grab one of these millions of p-hats. And you have to bet your life savings, right? You got to bet your life savings. Do you think that sample falls down here in the bottom 2.5? Do you think that sample falls up here in the top 2.5? Or do you think it falls in the middle? You got to bet your life savings. Where do you think that unknown p-hat's going to be? Well, my goodness, you're going to bet the middle, because 95% of samples are in the middle. So that's where I'm going to assume any random sample you find is going to fall. So listen, yes, there is a chance that we get a sample proportion that's significantly high or low, and then our interval would not capture the population proportion. But that is exactly why we're not 100% confident that the population proportions are in our interval. So again, let's break it down one more way. Sometimes this understanding, this picture I'm about to draw actually helps a lot of students. So remember, I don't know the true proportion that does fall in the middle of the sampling distribution. But I do know this. Right here's the cutoff between significantly low and normal samples. And right here's the cutoff between significantly high and normal samples. So as long as my p-hat falls anywhere in the middle, for example, maybe my p-hat falls right here. A little bit high, but not too high. When I build an interval by going up and down 1.96 standard errors, I'm going to capture the truth. Look, the truth was captured right around here. It was captured in my interval. Or maybe my p-hat is on the low side. My p-hat's down here somewhere, pretty low sample, but still normal. When I wrap my interval going up and down 1.96 standard deviations, look at this. I still caught the truth. Even if my sample was really, really high, but not significantly high, maybe right around here. Once again, when I build my interval going up and down 1.96 standard errors, I capture the truth. So sometimes I might capture the truth towards the center of my interval. Sometimes I might capture the truth towards the top of my interval. Sometimes it might be at the bottom of my interval. Regardless, it doesn't matter where in the interval the proportion is. It's just the fact that it's in there somewhere. That's the idea. And the only way, and I mean the only way your sample proportion will build an interval that misses the truth is if it's one of these super low ones. Like let's just say my sample came back way down here, very, very significantly low. And when I build my interval, I don't capture the truth. But listen, samples like that are very unlikely. I'm not going to worry about it. I'm going to bet my money that any p-hat I go and find by random is going to be somewhere in the middle. Hence, when I find my p-hat and I go up and I go down, I will capture the truth. A lot of people like to throw the word chance around. They like to say, oh, I know what 95% confident means. It means there's a 95% chance the truth is in my interval. Absolutely not. It actually has nothing to do with chance. It has to do with samples. 95% of samples are so close to the truth in the middle that when you build the interval around them, they will capture the truth. So it's actually, like, listen, with any interval, the truth is either in or it's not. There's no chance. There's no probability involved. It's either in or it's not. And there are millions of samples that are in this middle region. And of those millions of samples, all of them will capture the truth. It's not about maybe. They will capture the truth. The only ones that are not going to capture the truth are samples that are way down here or way up here. But I'm not going to worry about that. I'm not going to be negative Nancy. I'm going to focus on the 95% of samples that do capture the truth in the middle. So if we relate back to the question that we did at the last topic, the one dealing with what's the true proportion of infected sea fans in the Atlantic Ocean, right? If I ask you to build a 95% confidence interval, I hope based on the previous topic you found that to be pretty easy. But if I say to you, okay, explain to me what 95% confidence means, I hope you can now answer that question. Here is an example of what would be a really good answer. If we were to examine many possible samples of sea fans, each of size 55, then each sample proportion would create its own interval. 95% of these many intervals will capture the true proportion of infected sea fans, and yes, 5% will not. So that is why we can be 95% confident that the interval we found is one of the intervals that will still, in fact, capture the population proportion. So keep in mind, it's not about chance. It's not about probability. I'll even get students that say, oh, 95% of the time. Whoa, who said anything about hours or minutes or weeks or days? That's time, right? We're not talking about time. We're talking about samples. And there's millions of samples out there. We just know with 95% confidence of all those samples, ours is probably going to be one of them in the middle that catches the truth. All right, second topic in this video is focusing on the width of the interval. Simply put, more confidence means wider interval. Just think about that for a second. If I'm 90% confident, that means that the outside 5% at the top and the bottom, the 10% left out, are what's significant or unlikely. But if I increase to 99% confident, I have to go wider. I have to now say the top 0.5%, the bottom 0.5% is what's significant. So to do that, I went wider. So all other things the same, a 99% confidence interval is wider than a 90% confidence interval. So if you want a wider interval, become more confident. If you want a narrow interval, be less confident. Now listen, I don't know why anybody in their right mind would ever want to be less confident. Let me, for example, let's look at this, right? Let's look at this two ways. Okay. If I'm trying to estimate a population proportion, let's say I'm trying to find the proportion of students who study every single night. Okay. I could go super wide and I could say, listen, I am 100% confident that the proportion of students that study every night is somewhere between 0 and 100%. But what would the point in that be? Okay, yeah, I have high confidence, but I have no accuracy. Duh, any proportion is between 0 and 100%. So yeah, great, you're 100% confident, but that's a huge wide interval that doesn't give me any idea what the true proportion of kids that study every night is. Okay, another thing I could do is I could go super narrow. I could say, all right, I'm 20% confident that the true proportion of students that study every night is between 40 and 41%. Okay, listen, sounds like I'm being super accurate, right? 40 to 41% is a very, very tight window. It's only 1% wide. Seems very accurate, but it comes with the sacrifice of terrible confidence. Yeah, I have this very narrow window for where the truth is, but I'm only 20% confident the truth is in that window. That would just be plain dumb. So again, we like being more confident, but you have to understand that when you are more confident, say 95, 98, 99, you got to keep going wider and wider with your interval. But there is a secret. We can get the best of both worlds. Listen, hear me out on this, right? I want to be very confident. Like, I want to consistently do problems where I'm 98, 99% confident. You know, even 95 is okay. But I don't want to be down into the 80s. That would be terrible. I want to be highly confident. And what I just got done explaining was that if you want to be more confident, you got to go wider. Well, I also want a smaller interval because a smaller interval means I am more accurate. Well, believe it or not, there is a way to achieve both goals, to be more confident and still have a smaller interval. You want to know the secret? Bigger sample size. To achieve this goal of maintaining a high level of confidence but producing a small interval is to create a bigger sample size. Why? Because bigger samples vary less and should produce a sample proportion that is clearly closer to the truth. So a bigger sample with high confidence will achieve a narrow interval. Now let me kind of give you an understanding of why this is. Remember, the formula to produce an interval is p hat plus or minus the margin of error. The margin of error is your z star times the standard error, p hat, times 1 minus p hat, all divided by n. And the sample size is the key, because the sample size is in the denominator. And if you learned anything from previous math classes, it's this. When you divide by a bigger and bigger and bigger number, the overall value shrinks. So if I get a bigger sample size, like instead of using 100 students, I use 1,000 students, then this margin of error overall, because I'm dividing by the sample size, the overall margin of error is going to shrink. So I can still maintain a high level of confidence, but if I use a bigger sample size, I can get my margin of error to shrink, which means my interval shrinks. So bigger sample size is the key to having high confidence and still get a more accurate, small margin of error. All right, the next topic is how big of a sample do we need? Now, this is very, very common. Oftentimes, researchers will first determine the margin of error they wish to achieve and then determine the sample size they want to achieve that margin of error. Now, this is completely backwards, right? So what I'm saying is that instead of finding your sample first and then building your interval, you first start with saying, hey, I want a really small margin of error. Like maybe I only want a 2% margin of error. Up 2%, down 2%, that's only a 4% wide interval. That's pretty narrow. Well, how can I what size of a sample would I need to produce that super small margin of error? Well, the first thing that you have to do is make sure that you know the margin of error formula. The margin of error formula is equal to Z star times the standard error, which is, of course, the formula Z star times the square root of P hat times 1 minus P hat divided by N. This is the formula for the margin of error. So what I want to do is I'm going to give you a margin of error, or not necessarily I'll give you, but a researcher might say, hey, I want a given margin of error. I know my level of confidence, so I could find the Z star, and I want you to solve for the sample size. Now, the only thing that we run into is that if we don't even have a sample size, then we don't even have a sample. And without a sample, I don't even have a P hat. So what do I fill in for the P hats? Well, if you have nothing that indicates what it could remotely be, then you just use 0.5 for P hat, which means 1 minus 0.5 is also 0.5. So you just use 0.5 and 0.5 for P hat and 1 minus P hat. Let's look at an example of this. This is a very common AP test question. All right. Prior to an election, a mayoral candidate hoping to win against another candidate wishes to estimate the proportion of people in the city that will vote for him. He plans to construct a 95% confidence interval with only a plus or minus up-down 2% margin of error. How many people should he sample? So we have no idea what his P hat is, right? He hasn't even conducted a sample is. We certainly have no idea what the true proportion is. The election hasn't taken place yet, but he wants to create an interval that can estimate with a 2% margin of error what proportion of people will vote for him. So what sample size would he need? Well, I need to use my formula for margin of error, which is Z star times the square root of P hat times 1 minus P hat divided by the sample size. Now I'm just going to fill everything in. The margin of error he hopes to achieve is 2%, but we never use percentages. We always change them to a decimal in math, so 0.02. The Z star for 95% confident, I guess I should walk through this real quick just to make sure everybody understands. Z star is directly 100% tied to your level of confidence. So if I want to be 95% confident, what that means is I'm looking at the middle 95% of samples. 5% are left out, 2.5 at the top, 2.5 at the bottom. And that's the information I need. So I'm going to go to my calculator, second vars, go down to invert norm. Remember, invert norm will give you Z scores. All you have to do is tell it the percent at the bottom. So I'm going to put in 0.025 for the bottom 2.5%. And I get a Z star of 1.96. That's rounding it to 4 decimals, 1.96. Now you actually ignore the negative because actually remember the margin of error is plus or minus. So when you use it in the formula, you just use the positive value, 1.96. Now, what do I use for P hat? Well, again, he hasn't even taken a sample yet, so he has no idea what P hat is. So this is where we just put 0.5, and 1 minus 0.5 is also 0.5. And now we're going to solve for N. So here we just need some good old-fashioned algebra skills. Let's see, to solve this, the first step is to divide by 1.96. So I have 0.02 divided by 1.96 equals the square root of 0.5 times 0.5 divided by N. The next step is to get rid of the square root, so I'm going to square both sides. So I get 0.02 divided by 1.96 all squared equals 0.5 times 0.5 divided by N. The next step is instead of dividing by N, I'm actually going to multiply both sides by N. And if I multiply both sides by N, these N's over here cancel. So the final step would be just to divide by this weird number here, 0.02 divided by 1.96 squared. So N equals the 0.5 times 0.5 divided by 0.02 divided by 1.96 squared. Guys, it's not really that difficult of algebra, so hopefully you don't struggle with that too much. And all you got to do is type in the calculator exactly what we just found. So 0.5 times 0.5 divided by, in parentheses, 0.02 divided by 1.96. Close the parentheses, make sure the square's on the outside of that. And we get 2,401 people. So if this mayoral candidate interviews 2,401 people and asks them, are you going to vote for me in the election? Then he will create a confidence interval that has only a margin of error of 2%. Pretty easy, but a very common AP question. All right, the final topic in this video is actually the name of the topic of this video. How can we justify a claim? This is perhaps the best part of what a confidence interval can do. All right, suppose someone or some organization makes a claim about a population proportion. So an example, maybe a local police department says 88% of drivers in our city wear their seatbelt. Again, they make a claim. Maybe some scientist claims that 15% of the Earth's volcanoes are ready to erupt. Maybe some type of high school principal claims that only 12% of kids at my school vape. Whatever. A claim has been made with a proportion. Well, we could use a confidence interval based on a sample proportion to either justify the claim or confirm that the claim is unfounded. So this is the great thing, right? Somebody makes a claim. We could use a confidence interval to determine if that claim has any justification behind it. So think about it. All you have to do is find a confidence interval. So once you find a confidence interval, by following the procedure that we already learned, you're going to get a low number and a high number. Okay. So now, two things are going to happen once you have your interval. First, if the claimed population proportion falls within your interval, then that claim that has been justified might not be wrong, right? So for example, maybe I go into the city and I get a confidence interval of 0.83 to 0.92. So this tells me that what proportion of people wear a seatbelt in this city? Anywhere from 83 to 92%. So the police claim that 88% wear a seatbelt falls in the interval. So I guess their claim is justified. I cannot officially tell them your claim is wrong, right? Now, I don't necessarily know that they're guaranteed to be right, but the point is because 88 falls in my interval, I cannot say they're wrong. Their claim is justified. The second thing that can happen is that the claimed population proportion falls outside of your interval. So maybe you get an interval that looks like this, and your interval says that you're pretty confident that somewhere between 75 and 84% of people in the town wear a seatbelt. Well, now all of a sudden, their claim is unjustified, okay? Because their claim fell outside of my interval. So this tells me that their claim is unjustified and possibly wrong. Now, think about it this way as well, right? The only way that their claim could still be true, now make sure you process this, right, based on everything we've been teaching you, is that 88% is clearly outside of my interval. So the only way that their claim could still be true is if my sample that produced this interval was one of those extremely low ones. If it was one of those extremely low ones, those significant bottom samples, then yes, my interval would not contain their claim. But here is the rub. Samples like that, really low samples, are unlikely. So I don't believe that my sample is one of them. I'm always going with the confidence that the truth is in my interval. So therefore, I believe their claim to be wrong because their claim is not in my interval. So I would tell the police, hey, that's nice that you think 88% of people wear their seatbelt, but I bet it's lower. All right. Now that we have learned an awful lot about confidence intervals, we know how to build one, and we learned all these finer details, let's dive into what I consider an ultimate problem. This is a really good AP type problem. All right, here we go. PETA is the People for Ethical Treatment of Animals. They claim that nationwide, throughout all of the United States, 17% of all dogs are malnourished. Okay, that's their claim. Well, the Humane Society of Summit County in Ohio decided to conduct a sample to estimate the proportion of malnourished dogs in its county. Their sample produced a 96% confidence interval of 0.09 to 0.15. Let's answer the following questions. The first question says, whoa. What do you mean by 96% confident in this problem? Well, this is what we started off in this lesson talking about. When we talk about 96% confident, we mean 96% of all samples will produce an interval that contains the true proportion of malnourished dogs in Summit County. Remember, the sample that they're talking about came from a specific county. All right, so it's important that you understand it's not a 96% chance, it's not a 96 probability, it's not 96% of the time, it's all about 96% of samples. I'm just going to go with the assumption that my sample is one of them. Why wouldn't it be? 96% is pretty high. All right, next question. What does this interval actually tell us? Let's interpret the interval. The interval came back 0.09 to 0.15. Well, this means I am 96% confident the true proportion of malnourished dogs, sorry, my handwriting is just atrocious, malnourished dogs in Summit County is between 9% and 15%. Is it towards the top? I don't know. Is it towards the bottom? I don't know. It's either in or it's not. I don't really care where it's at. I'm just pretty confident it's in there somewhere. All right. What was the actual sample proportion that the Humane Society found? What was the actual p-hat? I'll get a lot of kids that will try to solve for it. They'll try to do some type of algebra. Whoa, 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 whoa. Back off. It's so easier than that. Listen, all you have to remember is remember how confidence intervals are built. You start with p-hat. You go up and you go down a margin of error. What that means is because you're going up and down by the same number, what that means is that p-hat will always, always, always fall directly in the center of the interval. So if I want to find the center of this interval, all I got to do is take 0.09 plus 0.15 and divide by 2, and you'll get the center. And that ends up being 12%. So the sample proportion that they found must have been 12%. So their sample of dogs must have had 12% malnourished. The next question is actually even easier. What was their margin of error? Well, remember, the margin of error is the amount that you go up and you go down from that p-hat. So now that I know the center is 12%, I clearly went up 3% and down 3%. Down 3% was the 9, up 3% was the 15. So the margin of error is 0.03. I'll get a lot of kids that try to do math. They try to use algebra. If you have the interval in front of you, you don't have to do any math. You just have to think. All right, the next question is how big was the sample that they used? Oh, this is a really good question. All right, what formula involves the size of the sample? The margin of error formula. Margin of error is the z star times the square root of p-hat times 1 minus p-hat all divided by n. So let's fill in everything we know. We just discovered that the margin of error was 0.03. If you want to be 96% confident, let's walk through this real quick because the level of confidence is directly how you find the z-star. 96% confident means 4% is left out. That gets split up because of symmetry, 2% the top, 2% the bottom. So when I use invert norm, I'm going to use the bottom 2% to get the z-star. It's going to come back negative because it looked at the bottom, but remember I just need the number itself, which is positive, or negative. It's actually both. 2.0537. All right, now the formula for the standard error is p-hat. Oh yeah, I already found p-hat, 0.12. The opposite is 0.88. I'm going to divide that by my sample size of n. So now that I filled everything that I knew in, I'm just going to solve for n. We already did this once. We'll do it again. First thing is divide by the 2.0537. Then I have to square both sides to get rid of the square root. Square root is now gone. I'm going to multiply the n over to this side because I don't want it to be on the bottom. So multiplying both sides by n will cancel it out. And then the final step is to take the 0.12 times 0.88 and divide by the 0.03 divided by 2.0537 all squared. All right, so 0.12 times 0.88 divided by, I need a parenthesis here. Whoop, I put minus, sorry. Divided by 0.03 divided by 2.0537. Close the parenthesis, square on the outside. And now remember, this was a sample of dogs. There is some rounding going on here because I did some rounding with my Z-star. So just round this, always round this number up because you're dealing with an actual number of objects, in this case dogs. So I'm going to round that to 495. So there is approximately 495 dogs in my sample. So it's pretty cool that if all you have is an interval, you could back solve and find everything else you possibly need. All right, the final question is actually the most important one. So with it at the end here, does the claim from PETA seem to hold true for Summit County? The answer, no. My intervals showed that in Summit County, the proportion of malnourished dogs is somewhere between 9% and 15%. The claim from PETA was that 17% of all dogs in the U.S. are malnourished. Now, listen, that might still be true for the nation. I'm not saying that PETA is wrong, but what I do know is that for Summit County, that claim does not hold true. In Summit County, I would gamble that the truth is lower than 17%. Because I believe, for Summit County, I believe the truth to be between 9 and 15%. So therefore, the claim of 17% does not hold justification in Summit County because it's not in the interval. Pretty easy. So, the final question was really what the topic was about. But boy, there's a lot of really good detail in this video. So please make sure you go back and pause and write down, copy, process, whatever you have to do, because there's 4 big ideas in this video, and all of them are super important moving forward when we work with confidence intervals. All right, guys, see you in the next video.